So what we know about the reactivity of the carbonyl compounds that we've talked about so far is that our acid chlorides are the most reactive, and our amides are the least reactive. And that will continue to be true. But now what we need to do is we need to put ketones and aldehydes into this reactivity spectrum. And so our aldehydes are going to be a little bit more reactive than our ketones, but overall ketones and aldehydes are going to fit right into the middle of this spectrum. So right after our anhydrides, this is where our aldehydes are going to go. Followed by our ketones. So what we have is our most reactive as the acid chlorides, on down to the least reactive, which is going to be our amides. So this is the reactivity pattern for the carbonyl compounds that we've talked about so far. Acid chlorides are most reactive, then anhydrides, then aldehydes, ketones, carboxylic acids, and esters are about as reactive, and amides as the least reactive. When it comes to the reactivity differences between aldehydes and ketones, we can use resonance in order to understand why our aldehydes are more reactive than our ketones. If we look at an aldehyde and a ketone, we know that both of these compounds have a significant resonance structure where we can pull the electrons up to the oxygen, and we can show electron density at the oxygen and a positive charge at the carbon. We can do the same thing here for the ketone. So that as we compare these two structures, if we look at this positive charge, here we have a positive charge that's being stabilized by this oxygen, a carbon, and a hydrogen. That's going to be a little bit less stable than what we have here for the ketone. So this positive charge that's stabilized by the oxygen and the two carbon-containing groups on either side. So overall, this resonance stability that we have on our carbonyl is going to contribute to the reason that our aldehydes are more reactive than our ketones. When it comes to the reactivity of ketones, there's a little bit of steric consideration that we need to account for. So that if I have a ketone like acetone or 2-propanone, where I have methyl groups on either side of that carbonyl, compared to a ketone like this one, where I have tert-butyl groups on either side of that carbonyl, we know right away that this ketone with the tert-butyl groups is going to have more steric hindrance. But the steric hindrance is really going to come into effect when we have to go from this sp2 hybridized carbon of the carbonyl to the sp3 hybridized carbon of the carbonyl. Because what's going to happen is that if I have a nucleophile come in and attack at that carbon, push the electrons up to the oxygen, I'm going to get to my tetrahedral intermediate, which looks like this. And in this structure at the beginning, this carbon that was sp2 hybridized, we had bond angles of 120 degrees compared to bond angles of 109.5 degrees once I form that tetrahedral intermediate. So that means that in three-dimensional space, these methyl groups are going to be much closer together in that tetrahedral intermediate. For the ketone right here, I see the same thing. It's not so much of an issue of the sterics when the nucleophile attacks the ketone, because this is an sp2 hybridized carbon, so that nucleophile can come in from the top face or the bottom face, and the sterics that we see here doesn't have a huge effect on that attack. But what we're going to see happen is that when this nucleophile attacks here, we're going to see this ketone react more slowly because that tetrahedral intermediate that forms now has to put these tert-butyl groups, our big bulky tert-butyl groups, closer together in three-dimensional space, again with bond angles of 109.5 degrees at that tetrahedral intermediate. 120 degree bond angles to start. So here we have to put our big bulky groups closer together. So that can be another reason that impacts the reactivity difference for a ketone compared to an aldehyde. So there's two classes of reactions that we're going to see for ketones and aldehydes. The first being reversible reactions, the second being irreversible reactions. For the reversible reactions, that's where we're going to start, and these are mechanisms that you should be able to work in both the forward direction and the reverse direction. When it comes to our reversible reactions, there's 5 reactions we're going to talk about. We're going to talk about the formation of hydrates. We're going to talk about the formation of acetals and ketals. We're going to talk about the reactions that form thioacetals and thioketals. We're going to talk about reactions that form imines and enamines. And finally, we're going to talk about reactions that form cyanohydrins. In each case, these reactions are reversible. We will go forward and backward. And in each case, the products that we form as a result of the forward pathway are going to represent new functional groups for us.